Hey guys, welcome back to High Tech 10s. Today we'll talk about why the James Webb Telescope's hard drive is actually pretty small. Let's head into it. Why so small? As Tom Stuff points out, it's almost difficult to compare hardware that operates in space orbit with hardware that operates on the ground. A standard hard disk would be quickly damaged in space due to the extreme differences in temperature and pressure. How does NASA get around the problem? According to Alex Hunter, a flight systems engineer at the Space Telescope Science Institute, the storage is largely for short-term use and only has to suffice for roughly 24 hours. In order to transmit the images back to Earth, JWST is expected to travel a distance of around 1.5 million kilometers, or 932,000 miles. According to IEEE Spectrum, 3% of the capacity is designed for engineering and telemetry data, and the storage size is expected to decrease to 60 gigabytes in around 10 years' time. In spite of the telescope's lack of storage capacity, it makes up for it in other areas. At a wavelength of 28 micrometers, the JWST's 25 square meter primary optic can catch infrared rays. Although NASA has not stated the reason for the telescope's storage capacity limitations, it is possible that the telescope is just beyond its prime. The project's earliest concepts started in 1996, and the first contract for its production was signed in 2003. A total of 57.2 gigabytes of data is delivered every 8 hours by the James Webb Space Telescope, which demonstrates that the current size of the hard drive is adequate. Engineering experts predict the JWST drive will have 60 gigabytes accessible after 10 years of operation, thanks to circumstances in space. That's pretty amazing, right? In any case, the newest NASA telescope is a technological marvel that will help us in our quest to better understand our cosmos. James Webb Space Telescope's first images explain what we've already learnt: intense clarity. US President Joe Biden gave a sneak peek of Webb's deep field at a press conference. Galaxy cluster SMACS 0723 consists of hundreds of galaxies around a single super bright galaxy that squats at the center. The numerous elongated arcs, which reflect background galaxies that have been gravitationally lensed by the cluster's bulk, will quickly catch your eye. In other words, gravity has warped or stretched and amplified the light from distant galaxies, resulting in a vastly magnified view of the cosmos. The sharpness of the photographs, particularly when seen through the lens, is astounding. Astronomers have nicknamed this spiral galaxy the Slug because of its location in the deep field. The SMACS 0723 cluster is many times further away. However, we couldn't help but focus on the razor-thin arc immediately above, marked with arrows. Webb's strength is evident even in this little sliver. Webb is able to plainly observe the beads on a thread that Hubble missed. Most likely, they are separate star clusters in a faraway galaxy. In the deep field, the details are just as stunning. Webb is intended to be more than 100 times more sensitive than Hubble when it comes to point-like objects, and this clearly proves that. Revealing hidden elements. Infrared spectroscopy, where light is split down into wavelengths to disclose an object's composition, is also a capability of Webb's. Unlike Hubble, Webb does an excellent job at this, as seen by the spectral image of the huge planet WASP-96b. Nearly half the mass of Jupiter, this planet is 1,120 light-years distant. When the spectrum dips, water vapor is present in the atmosphere of the planet. WASP-69b's closeness to its parent star means that it is unlikely to support life. It's amazing because this technology can be used to find any of the 5,000 plus additional exoplanets that have been discovered. One day, we may be able to detect biomarkers like ozone and methane using spectroscopy, seeing dust and gas. The third picture is of a region of the Milky Way called the Southern Ring Nebula, which is located around 2,000 light-years distant. This picture demonstrates Webb's capacity to see in the mid-infrared spectrum. It is an excellent illustration of a planetary nebula, which is a kind of nebula in which the core star has shrunk to the size of a white dwarf as a result of the loss of its outer shell. This takes place at a pace of around 15 kilometers per second, releasing rings of gas and dust into the atmosphere. This white dwarf is the fainter partner and can only be seen in the mid-infrared because it is shrouded by dust. The brightest star in the center is really a companion star, and the white dwarf is the fainter partner. The dust that is being generated as a result of the expanding gas is likewise brought to light by the mid-infrared. What do you think about the James Webb Telescope? Let us know in the comment section. This brings us to the end of our video. I hope you enjoyed it. Hit like if you did, and don't forget to subscribe to our channel so that you don't miss any of our videos in the future. Also, watch the 2 videos that are on your screen because I'm sure that you'll love them. And with that, I'll see you in the next video.